Welcome, everyone. So, as a researcher, I read a whole lot of supply chain literature. But today, we are diving into a genuinely groundbreaking peer-reviewed paper. It's called Green EOQ with Cold Chain Switching and Batch Jumping under Piecewise Carbon Pricing. I know, it's quite a mouthful, but stick with me. This study fundamentally rewrites how we model logistics, energy trade-offs, and carbon emissions. It is absolutely fascinating. Let's get right into it.
Okay, so what's the big problem we're trying to solve here? Well, let me point out a critical flaw in the current academic literature. The classic economic order quantity, or EOQ model, basically assumes a perfectly linear cost structure. It's neat, it's tidy, but it completely ignores the harsh realities of modern, punitive carbon taxes. Plus, it completely fails to capture the massive energy consumption differences between cold chain and ambient temperature logistics. Basically, traditional EOQ is mathematically disconnected from the real world. We desperately needed an upgrade.
Here's a research outline for today's explainer. We'll start by unpacking those traditional inventory blind spots, then walk through the three stages: the baseline model, cold chain and energy, and the piecewise carbon tax. After that, we hit the really exciting part, a key finding called batch jumping, before wrapping up with practical conclusions.
All right, Section 1, Traditional Inventory Blind Spots.
Historically, carbon policy modeling has been completely static. It just didn't account for exponential tax jumps based on actual emissions. On top of that, cold chain and ambient systems, they were studied in total isolation. Geographic localization was practically ignored, and there was just a complete lack of dynamic policy integration. Modern supply chains have moved way past simple, single-cost optimization. We need models that actually reflect that real-world complexity.
Moving right along to Section 2, Stage 1, our baseline model.
To really unpack this, the researchers built their mathematical logic in three distinct steps. First, establishing the baseline EOQ. Second, injecting those cold chain energy costs. And finally, unleashing distance variables along with a piecewise carbon tax. Structuring it this way lets us see exactly how environmental factors progressively warp traditional decision-making.
The absolutely crucial thing to grasp in Stage 1 is the pure, uninterrupted math. The baseline EOQ calculates a static, optimal order quantity by simply balancing fixed administrative ordering costs against basic warehousing holding costs. In the paper's numerical example, this optimal baseline lands right at about 7,071 units. Now, at this stage, without any environmental factors plugged in, ambient and cold chain optimal orders look mathematically identical. There is literally zero distinction yet.
Section 3 brings us to Stage 2, cold chain and energy.
Here's where it starts getting interesting. The researchers introduced a brilliant binary switching factor. They call it K. When K equals 0, we're dealing with ambient temperature materials. Normal holding costs, nothing crazy. But when K equals 1, the cold chain is officially active. Suddenly, boom, extra electricity and energy consumption costs are slammed right into the denominator of our formula. To translate this math into actual human behavioral motivation, the massive holding cost of cold chain electricity mathematically forces companies to minimize their warehouse inventory. It pushes them into this very small quantity, high-frequency replenishment model, just to keep the electricity bill from exploding.
Now for Section 4, Stage 3, piecewise carbon tax.
This punitive, stepped carbon tax function perfectly mirrors real-world regulations. Think of the European Union's CBAM, right? It is not some smooth, flat fee. If your transportation emits 5 tons or less, it's a manageable $50 per ton. But between 5 and 8 tons, that penalty quadruples to $200. Break that 8-ton threshold, and you are slapped with a massive $500 per ton. Because this cost function is so jagged, it's non-smooth, you literally can't use a single mathematical equation to find your optimal order quantity anymore. The math becomes wildly disconnected.
Which brings us to Section 5, and honestly, the absolute climax of the paper, the key finding: batch jump it.
Let's walk through the actual numbers here, because this is where the magic happens. In Stage 1, the baseline for both ambient and cold chain materials is exactly 7,071 units. Then in Stage 2, high warehouse electricity costs push the cold chain order down to 6,324. But in Stage 3, when that punitive piecewise carbon tax kicks in, something unbelievable happens. The ambient material order shifts just a little bit, down to 6,850, but the cold chain order, it radically shifts from 6,324 all the way up to exactly 10,000 units.
I mean, think about that dramatic leap.
6,324 units skyrocketing straight up to 10,000 units. Why on earth does the model do that? Well, because it's 6,324 units. Those frequent transport trips were pushing total carbon emissions right up against that brutal 8-ton penalty bracket. To dodge the massive $500 per ton carbon tax, the math essentially recalculates the entire strategy. It decides it is actually cheaper to order a massive batch of 10,000 units, drastically slash the transport frequency, and just eat the extra electricity costs in the warehouse.
This core phenomenon is what the researchers beautifully coined batch jumping. It's a discontinuous shift where companies drastically increase their order quantities. They do this specifically to reduce transport frequency and completely dodge those punitive carbon tax brackets. It happens precisely when the marginal increase in carbon tax costs severely outweighs the trade-off of paying for more cold chain warehouse electricity. This proves mathematically how strict environmental policy fundamentally distorts standard supply chain behavior. It's a real game changer.
Finally, Section 6, Conclusions and Practical Applications.
So what are the actionable takeaways you need to know? First off, distance is an absolutely crucial make-or-break variable. The model proves that drastic reductions in transportation distance, which really means localized procurement, can powerfully offset those high cold chain energy holding costs. By sourcing locally, you drop your transportation carbon footprint and you avoid the tax brackets entirely. And this isn't just theory either. It mathematically validates real-world strategies from industry giants like TSMC, who are heavily investing right now in localized supply chains. Ultimately, this multi-stage model is a vital quantitative tool for any corporation actively pursuing 2035 carbon neutrality goals.
We've covered some incredibly dense, fascinating mathematics today. We've seen exactly how environmental policies literally rewrite the rules of inventory management. So I want to leave you with one final provocative question to think about. If your cold chain logistics trigger a severe CBAM penalty tomorrow, does your mathematical model actually know how to jump, or is it going to sink under the weight of static, outdated equations? I highly recommend diving into the full paper to ensure your supply chain is resilient enough for the future. Thanks so much for joining me, and keep learning.